Go.
Hello, everyone. I'm Dang, and my project partners are.
Ibrahim Bitar.
And Dominique Vaca.
And today we're presenting our project titled Full-Duplex for Low Power IoT, a survey and analysis of FD-LoRa. Our goal is to explain why full-duplex matter for LoRa, how FD-LoRa works, and what research challenges still remain. Ibrahim, can you go to the next slide? To understand why full duplex matters, let's start with LoRa's limitations. LoRa today is half duplex, meaning a device can either transmit or receive, but never both at the same time. This creates noticeable problems. High latency, especially because downlink packets are forced to wait for receiving windows. Collisions, since gateways can't respond immediately. Reduce responsiveness, especially for time-sensitive IoT applications. So the motivation is simple. If LoRa could operate in full duplex, it could dramatically reduce latency, improve ACK reliability, lower congestions, and make the entire network more responsive. Ibrahim, may you go to the next slide? Full duplex base means transmitting and receiving at the same time on the same frequency. But this is extremely difficult because your own transmitted signal is millions of times stronger than what you're trying to receive. So full duplex requires self-interference cancellation, or SIC. Without SIC, the receiver would be completely overwhelmed by transmitter's own signal. In contrast, half duplex avoids this problem by never transmitting and receiving simultaneously, but that's exactly what limits LoRa's performance. Ibrahim, may you go to the next slide, please? LoRa Class A timing. Here's the major bottleneck in Class A. It nodes transmits, and then it must wait for receiver 1 and receiver 2 receive windows, which opens 1 and 2 seconds later. This delay is unavoidable in half duplex, so even a simple acknowledgement takes seconds. For time-sensitive applications like actuation, alarms, or reliability, critical IoT, this hurts performance. Full duplex removes these receiving windows entirely and allows immediate downlink. Ibrahim, may you go to the next slide, please? For here, we're talking about the SIC overview. To achieve full duplex, FD-LoRa uses a 3-stage cancellation process. Passive suppression using antenna arrangement and signal isolation. Analog cancellation, which subtracts a phase-aligned copy of the transmitted signal before the ADC. Digital cancellation, which reconstructs the transmitted chirp and subtracts errors in the digital domain. Combining these stages reduces interference by more than 50 to 60 decibels, enough to allow LoRa reception without transmitting. And I'm going to hand over to our next speaker, Ibrahim, for our prior work.
All right, everybody, I'll be taking over. This is Ibrahim. So before FD-LoRa, full duplex communication had already been studied in other wireless systems. The first breakthrough came from Mobicom in 2010, which proved full duplex was possible through analog cancellation. Then Sitcom in 2013 improved both analog and digital cancellation, making full duplex more practical. And then more recently, Mobicom in 2020 demonstrated full duplex in millimeter wave bands using beam isolation. FD-LoRa builds on these ideas, but adapts them for chirp spread spectrum and low power radios, which is significantly more challenging. FD-LoRa is notable because it works on real LoRa hardware, specifically SX127X radios, without modifying the PHY layer. It achieves full duplex with a single antenna and a two-stage cancellation pipeline. The key insight is that LoRa's chirp structure is predictable, so the system can reproduce the transmitted chirp for cancellation. Because FD-LoRa doesn't change modulation or the LoRaWAN protocol, it's compatible with existing networks, making this approach practical. In the analog stage, FD-LoRa generates a copy of the transmitted chirp and aligns it with the interference on the receive path. Two parameters matter: the phase alignment and the amplitude attenuation. If aligned correctly, the system can remove about 30 to 40 decibels of interference before the ADC. This prevents the front end from saturating and makes digital cancellation feasible. The digital stage handles residual interference that analog cancellation couldn't remove. The receiver demodulates the chirp, estimates carrier frequency offset and phase errors, and reconstructs the transmitted signal with high precision. Subtracting this reconstructed chirp removes an additional 20 to 25 decibels of interference. Together, the two stages provide enough cancellation for full duplex LoRa communication even under low SNR conditions. And then I will be handing over the slides over to Dominique.
Hi, everyone. We are now reaching the closing part of our presentation, beginning with the evaluation results. So jumping off what Ibrahim has mentioned, we received a 4 times improvement of the acknowledgements. So essentially with the self-interference cancellation in place, the packets are correctly acknowledged far more often on the first attempt, about 4 times as many. This reflects better reliability without changing the LoRa physical layer or the MAC framing, which is the media access control. Secondly, this also reduces the number of retransmissions, which also improves congestion. Because more packets succeed on the first send-off, we trigger fewer retries. This directly lowers the channel occupancy, which means less contention, back-off, and collisions. It shortens queuing delays for subsequent traffic as well. It's a cleaner channel and smoother end-to-end performance. And this also is more robust, which means that it can work for SF7 to SF12. SF meaning the spreading factor or the trade-off between power consumption, data rate. And this even works for lower SNR. We validated the design across the common spreading factors at lower SNRs where standard links typically struggle. This analog and digital cancellation still preserve decodability. So the gain holds from faster SF7 to SF8 to longer range SF11 to SF12 modes. Ibrahim, could you please go to the next slide? Thank you. Now, despite these massive gains, there are important constraints to keep in mind. First of all, we have to deal with phase drift and CFO sensitivity, the carrier frequency offset. Our cancellation quality depends on accurate phase and carrier alignment. Drift over time or temperature degrades suppression and can raise the residual self-interference floor. In addition, we also need to keep in mind the environmental dependence. So dealing with multipath and placement really matter with respect to LoRa. Changes in the nearby reflections or antenna orientation can alter the self-interference channel, which means the tuned analog canceller may need adjustment to maintain its robustness. Now, dealing with cancellation depth below Wi-Fi full duplex systems. Compared to wideband Wi-Fi FD prototypes, our total in self-interference cancellation is less robust. So it is still sufficient for LoRa's narrowband domain, but it leaves room for stronger analog suppression and smarter digital modeling. Our results focus more on the single link behavior, but coordinating simultaneous full duplex across many nodes without creating new interference is still an open problem. Ibrahim, would you mind changing slide? Now, to wrap up, FD-LoRa makes full duplex feasible on commodity LoRa. With passive analog and digital self-interference cancellation, we can transmit and receive concurrently on the same channel. It does deliver meaningful reliability and latency benefits, which is a huge improvement. With more first try acknowledgements and fewer retransmissions, this translates into a lower congestion and shorter delays, which is a huge practical milestone. Now, this doesn't mean that everything has been solved. We still have a richer research agenda to go over to improve cancellation, adapting to dynamic moving environments as well, and scaling to multi-node full duplex operation are still active challenges that require more development and research. And that is the end of our presentation. We thank you for watching.
Thank you all.